So some of the problems on the homework involve economic problems, and for those problems we're oftentimes wanting to like maximize the profit or minimize the cost. And so here's an interesting one I found. I don't think there's one quite like this on your homework, but it's a good one. And one reason I like this is that you really have to pay attention to the units. And you have to make sure all the units line up. And that's a very helpful thing when you're setting up your equations, to make sure the units work out. And this is a good problem to see that. So basically this says the cost of fuel to propel a boat through the water in dollars per hour is proportional to the cube of the speed. And we're going to say the speed is miles per hour. And so at 10 miles per hour it costs $100 of fuel per hour. Okay, so at 10 miles per hour you're going to have to pay $100 of fuel per hour. So in addition to fuel, it costs $675 per hour to run the boat. So suppose the boat is like a ferry or a cargo boat or something like that. And so that's a cost that would go to like labor, maintenance, etc., things like that. So so it's the cost of fuel plus $675 per hour to run this boat. And so what it wants to know here is what speed should the boat travel to minimize the cost of running the boat in dollars per mile. So that's key here. What speed should the boat travel to minimize the cost per mile traveled? So our final equation that we're going to minimize has to be cost per mile. Okay, so let's start here. And I'm going to use, I don't know if I'm going to need all these variables, but we do rate times time is equal to distance, right? So R could be rate, T, time, D, distance. But our equation, we want to know what speed we're going to minimize the boat. So our equation, the final variable is going to be R. And that R here is going to be, miles per hour. And, but our equation is going to need to be cost in dollars per hour. So our cost, and I'm going to say cost total. So because we're going to have cost for fuel plus all those other costs, which I'll say C naught. Okay, and this is going to need to be in dollars per hour. By the way, I'm going to make this look very simple and easy. This was not an easy problem for me to solve. I had to sit and really think about it and break apart these units. And then I had to go back and redo it and think about how I would share this with you. So just because I make it look easy does not mean it's this easy. These can be very hard to think about, and you have to sit and really think here. Okay? So what I want to do is I want to look at each of these. So that cost for fuel, what it tells us here is that it's proportional to the cube of the speed. So R is the speed, and so this is proportional to the cube. So there's some constant times R cubed that gives you the cost for fuel, okay, per hour. Well, it tells us that at 10 miles per hour it costs $100 of fuel per hour. Okay, so what that means is it's giving us a value here. It's $100 to run the boat for an hour when the rate is 10 miles per hour. So I can plug this in and I can actually solve for K, right? So 100 is equal to K times 1,000. So it looks like my K is equal to 100 over 1,000. So my K is just 1/10. So then I can rewrite this cost F is just equal to 1/10 R cubed. Okay? Well, what about the cost for everything else? So I want this to be dollars per hour. Well, this is dollars per hour. So it's simply the cost for everything else in dollars per hour is it's a constant. It doesn't change. It's $675 per hour. So So this is like dollars per hour. This is dollars per hour. So they match up. So it looks like my CT is going to be 110 R cubed plus 675. So again, I'm making this look easy, okay? But this is the cost total. Now, I'm not minimizing the cost in dollars per hour. I'm not finding the speed that gives me the minimum cost in dollars per hour, but dollars per mile, okay? So this is dollars per hour, but I want my thing to be the cost, and we'll let this be capital C. And this capital C, I want this to be dollars per mile. Okay, well, how do I go from dollars per hour? So, how do I go from dollars per hour to dollars per mile? Well, let's think about this. I want that to stay put, okay, but I want the hours to go away, and in its place I want miles to take its place. So what I can do is, can I divide anything here? So in other words, if I have dollars per hour, is there anything I could divide by that's going to give me dollars per mile? Well, whatever I have, I'm going to invert and multiply. And I want the hours to cancel out, and I want it to leave me with miles in the bottom. So you can see that this question mark is really going to be miles per hour. Looking at this. Then if I invert and multiply, the hours cancel out. I would have this. Hours per mile. These would cancel out, and it would give me dollars per mile. And that's what I want. So what it looks like is I have to divide this thing by miles per hour. So what is miles per hour? Well, that's the rate. So what I have to do is I have to divide the whole thing by R. So the real function that I want is 1/10 R cubed plus 675. All of that divided by the rate. And that's going to give me dollars per mile. It took me a little time to figure that out. Not obvious, and I'm sure I made that look easy. But this thing then, I could simplify this, and it would just be 1/10 R squared plus 675 over R. And so this is the equation, the cost equation, where you put in the speed, you get out the cost in dollars per mile. Okay? And so we really had to pay attention to those units. So now, what R gives me the smallest number of dollars per mile? Well, let's take the derivative. dC over dr is going to be 2/10 R. And this is going to be minus 675 R squared. Okay, well, I can set this equal to 0. And what I can do is I can factor out an R. And if I do this, this becomes 675 R cubed. Okay, so you get R is equal to 0, so that would minimize the cost if the boat's not moving, I guess. Or you could have 2/10 minus 675 R cubed equals 0. And by the way, that's a little confusing, but if you redistribute it, you see that the R would cancel out the one on the bottom, leaving you with that. So that's what I do. When I factor out, I always redistribute to make sure I get what I started with. Okay? So now, let's solve this. So 2/10 is equal to 675 R cubed. And so I'm going to move this up there and invert and multiply that over there, so it's R cubed. is equal to 6,750 over 2. And this over 2 is like 3,375. That's what this is. So my r is just the cubed root of 3,375. And if you plug that in, that's actually works out really nice, which is a miles per hour. It's nice when it works out nice, because in textbook examples it usually does work out nice, and it kind of lets you know you got it right. And so 15 miles per hour, but gotta be careful here. We know that's a critical point. We don't necessarily know that it's a minimum. Okay, so what I need to do is I need to take the second derivative here, and I don't know, can I fit it on here? Basically, when I take the second derivative, this goes down. I'm really squeezing this in. dr squared. I get 2/10. So this would be plus, and this would be 675 r cubed. And so this is what you would get. Putting this in there is going to make that greater than 0. This is always going to be greater than 0 for any positive miles per hour. And when it's greater than 0, it's concave up, making it a min, which is what you want. So it looks like this company is going to want to travel at 15 miles per hour in order to minimize the cost. So that is a nice problem, and it's a good one for thinking about setting things up and paying attention to the units to make sure you actually get the right answer. So, okay, well, very good.